Hi, welcome to the exercise for the lecture of bisoxazolines and reductions. Okay, and we can start with the first that say without the final compound and the transition state with the right stereochemistry. The first exercise is a cyclopropanation between this alkene plus this azoester. Okay, as a catalyst, we have copper triflate plus this bisoxazoline Okay, well, the first step that we need to do is to build the complex. That means, as you see, the copper coordinates with the two pair of electrons of the nitrogen, okay? And now, if you remember, what we need to do is to coordinate the diazoester. Remember that what is happening is that the copper is introduced in the diazoester, is inserted in the diazoester, forming a carbene. Okay? That means, remember that in this case, in the plane of the whiteboard, we have the bisoxazoline, okay, and the carbene is perpendicular to the bisoxazoline. That means the ester is coming in our direction and the hydrogen is coming inside. And now the only that we need to do is to know how is coming the alkene. Well, the alkene has to approach from one of these two sides. Which side will be? Okay, normally the side that will come there, this will be the side that presents less steric hindrance. Okay, first, from where will come? Okay, will come from behind the whiteboard or in front of the whiteboard. Okay, if it's coming in front of the whiteboard, he's crashing with the ester. Okay? If it's coming from behind, it's crashing with the hydrogen only. That means that will come from behind, and then which side of both will be? Well, if it's coming from behind, in this case, what is happening is this crashing with this phenyl. However, if here is coming from behind, what is crashing is only with this hydrogen. That means it's more stable, that is coming from behind and in this side. Okay? That means that will come from behind and in this side. And remember that because has to be overlapping between the p orbitals of the alkene and this orbital of the carbene, that approach will be perpendicular, will be parallel to the diazoester. The approach of the alkene will be parallel to the diazoester or perpendicular to the bisoxazoline, right? maybe you decide why I decide that the only way to decide if it's going in front of the slide or behind the slide is the ester. Why we don't consider that it's two phenyls? Because these two phenyls we have one in each side. That means approaching from where it's approaching, from in front or from behind, always will face one phenyl up, one phenyl down. That means they are no different. This is why it's a C2. Okay, then we have this. How we'll approach the double bond? What is the orientation of the double bond? Will be like this. Will be with the phenyl ring as far away of the phenyl and of the ester. That means that we'll approach, if we put it in 2 dimensions, we'll approach like this, okay? Perpendicular and with the phenyl down. And the phenyl not only behind the whiteboard but also pointing down in order to avoid all the bisoxazoline. That means if we have this, the only that we need to do is to draw the new bonds. Okay, that means that this will lead to, if we are doing it well, this phenyl is going down, okay, hydrogen up, and in this case the ester is going up and the hydrogen down. This will be the final configuration of the cyclopropane. Okay? Again, how we decided? First, we draw the transition state with the carbene inserted in the copper. Okay? And then we decide if the ester is up, this has to be approached down for which side. If approach down for this side, it's crashing with the phenyl. If it's approaching from behind here, it's only crashing with the hydrogen. This will be more favored, and then putting the phenyl ring as far as possible of the steric helium ends. Another question that you can have: why put the ester up? Well, you can put it down. It's exactly the same. You will get the same result at the end. Please check it at home. Why? Because this ligand has a C2. Okay, you don't have to worry how we put this, because both positions, with the ester up or with the ester down, is exactly the same. Okay? Good. Then, okay. We go for the second one. The second one basically is, we have this compound. Okay, this position is electrophile. Okay, it's a Michael position. We add a nucleophile, in this case a thiol, and as a catalyst we put copper triflate and the same bisoxazoline that we got before. Okay? Well, and in this case I told you that the geometry of the transition state will be square planar. Okay? Well, what we need to do first, we need to build the transition state. Remember, we coordinate the copper, and then we need to coordinate this, the starting material, by 2 positions. That means we need to coordinate by this carbonyl and this carbonyl. If we do this, mistake. We generate this complex here. Okay? If it's a square planar, it's all the bisoxazoline and the ketoester are in the plane of the whiteboard. What will happen is basically the nucleophile will attack the double bond. For which phase? Okay, if we check the transition state, the double bond is in the plane of the whiteboard, and from behind we have the phenyl. This phenyl will block anything that is coming from behind the slide. That means that the thiol will have to come from in front. If we do this, what we get is this final compound. Okay? Right? Okay. One question that you can have, why I put this configuration, that means, why I coordinate the ketone in this position and the ester in this? I can do it opposite? Yes, you can do it opposite, and you will get exactly the same final compound. Why? Because this is a C2. The ligand is a C2, that means that if you put it like this or you put 180 degrees, you will get exactly the same final compound. Please do it at home. Okay, the cert of bisoxazolines is very similar. Basically, the only that differs is that we put, now instead of copper, we have a zinc. Okay, what is happening? I told you that if a zinc, in the exercise, I told you that it's tetrahedric. What we need to do exactly the same, we coordinate the zinc now, and now when we coordinate the ester, what we have to do it is in a tetrahedrical position, that means. And now it's more difficult. Now, if it's in a tetrahedrical position, means that the bisoxazoline is on the plane of the whiteboard, but the ketoester is perpendicular to the whiteboard. Okay, and again, I put the ester in front and the ketone inside the whiteboard. You can do it at the opposite, yes, you can do it, it's not a problem. It's a C2, you will get the final same result. Okay, if I put here, okay, the double bond is inside the whiteboard, I have to check which side will be more available. If I come from here, from this side, from this face, I am crashing with the phenyl that is just blocking one of the faces of the double bond, because the phenyl here is inside. Okay? If I saw in this phase, what is happening is that this phenyl is blocking this ester, but it's not blocking the double bond. That means that the nucleophile will attack from this side. If the nucleophile attacks from this side, the final product will be this final product. Okay? Looks a little bit difficult, but if you do it with molecular models, it's by far easier, because here the problem is that this is perpendicular to the whiteboard and it's difficult to draw it. Okay, but this is how to do the exercise if we have a hot tetrahedral transition state or a tetrahedral geometry in the transition state. Okay? Good. Then, now we will go for the reductions. Basically, the first reduction is here. We are using this ketoester, R-binap, and hydrogen, ruthenium chloride. How we have to do it? Remember that the ruthenium has an octahedral environment. That means we put the ruthenium here. And here are the 8 positions. The phosphine, we put it behind. Okay, and we put the ketoester just in front. Okay, in order to have an idea, this is perpendicular. These 4 positions is perpendicular to the whiteboard. That means that the ketoester is here, planar like here. Okay, is on the paper. Okay. Then this is the information that I give you. The R-binap has this cycle that tells us from where it's transferring the hydrogen. Okay? In this case, if this thing means that the hydrogen can only be transferred or down here or up here. Yeah, because are the only white positions in this cycle. I mean, we draw it here, the hydrogen, the chloride. Okay, remember that we can put the hydrogen where you want. Okay, but in this case, because the approach has to come from this side, has to be down. And then it's attacking here. From behind, if this is planar, it's attacking from this position. Why? Because this cycle indicates that it has to be down and on the left. Again, you can ask me, why you put this coordination with the ester on the right and the ketone on the left? You can do it opposite. You can put the ketone here and the ester here and you will get the same. The only difference now is that the hydrogen attack will come from from right up. Okay, exactly the same, and you will need to draw the hydrogen up and the chloride down. But it's exactly the same. If this happens, what we have, this is attacking from down, that means that okay, this is the final configuration of the compound. Please repeat it. If you want to repeat it at home, it's better that you put it opposite and check that you will get the same configuration. Okay? Good. Then the last one. What we have now is a CBS reduction of this ketone. We add the catalyst, Okay, and borane. What we need to do first, we need to build the transition states. Remember that the borane coordinates with the amino alcohol, and what we form this, okay? And then a second molecule of the borane is coordinating the nitrogen, okay, forming this, that is the active catalyst for the reduction. Then what is happening? From here is coming the ketone. How is coming? From behind, because we need to avoid the steric interaction with this methylene, diphenylmethylene, and with the big group. This is the large group, this is the small group, okay, obviously one is a methyl and one is a phenyl. If we put it like this, large group down to avoid this now is here, is perpendicular, and the small group up. Okay, this is coming perpendicular like this. And then simply the hydrogen is transferred to the carbonyl group. If we do this, what we got is we got this configuration that is the same. Okay? I understand that this can look confusing, how we orientate the molecule, but it's only a question of a lot of practice. I mean, if you repeat the exercise, you will see that at the end you will be able to draw this perfectly without any problem. Okay? And that's all for today. This was the exercise. Please try to repeat it, try to put it in the not in this case, but in the other cases, in the opposite orientation, and you will see that you will get the same as me. If you don't get the same as me, or you have any question, feel free to send me an email or ask me in the Friday lectures, or we can organize a meeting one-to-one, whatever you prefer. Thanks for your attention, and see you soon.